Hey engineers, and welcome to 1.2.3 Series and Parallel Circuits Concepts. Today what I'm going to do, I'm going to try to get away from and not involve any math, but just to take you through what a series circuit is and what a parallel circuit is, and what makes them similar, what makes them different, and why, and try to explain why they behave the way that they do inside of a circuit. So let's get started. First thing, a series. A series circuit is when there's only one pathway. That seems pretty straightforward. Well, or then a parallel, obviously, when there's more than one pathway. For the current to travel. This is the main idea between series and parallel. I'm going to jump over to our simulator over here, and I'm going to build a series circuit. So here I am. I'm going to hook up 3 resistors in series. And I'm actually going to put a switch in here so you can kind of maybe understand exactly how a switch works. And here we go. I'll try to make nice, easy number. Well, we'll just not have any numbers, but I want to have lots of voltage first of all. Lots of voltage so we can see here. It's a lot of push. So then each of my resistors, I think they default to 10 ohms, right? So if you look here, this is a series circuit right now. I'm going to write series up on the board so it's always with us. This is how you hook up things in a series circuit. There's only one pathway for the electricity to flow. And if you break that path anywhere, like this switch, I click on it, it opens up the pathway. The current stops everywhere. Close the switch, open the switch. It's open. This is called open. This is closed. When I open this circuit, it stops the current everywhere. And I bring over my current, and if I break the circuit here and I insert my meter, it measures 2.45 amps. So I can rebuild my circuit. I'll insert my meter here. I'll try anyway. 2.45 amps. Now remember, whenever you measure current, we always have to break the circuit. You have to cut the circuit, open it up, and you'll notice that the current stops everywhere. I'm going to bring in my 2.45 amps. Now, there's an easier one to use, but I don't like it because it's not like true to life. I can see 2.45, 2.45. No matter where I measure the current, it's always the same. It's the same everywhere inside of a series circuit. Now, in a series circuit, you can think of a resistor as a kink in the hose. So if I kink this hose, I'm going to increase this resistance here, and watch what it does to the whole thing. So I just tripled this one's resistance. Did you see how the current slowed down in the entire circuit? I could increase this one. Just tripled that one. Triple this one. So doing something to one resistor or one of these components has an effect on the whole. So if I kink this one, it slows down the current everywhere. Because there's only one pathway for this electricity to go through, putting a larger kink here affects the whole. Now let's talk about pressure. So voltage is like pressure, and I think that my battery, let's make it a nice round number. Let's maybe make it, I'll go 90. So when I put this on here, I should get 90 volts. But when I put this across this resistor right here, I get 30 volts. And I did it backwards, that's why it's negative. 30 volts. And when I go across this one, it's also 30 volts. And when I go across this one, it's also 30 volts. So this is splitting the voltage. There's an equal amount of pressure here, here, and here. The pressure gets divided between them. Now, if I increase the resistance here maybe to 60, so I'll double this resistance. Now let's look at the pressure. The pressure here has now gone up to 45. There's more pressure here. If you think of a hose, and the harder you kink the hose, the bigger the pressure difference on the upstream side and the downstream side of that hose. That's why this voltage is working the way it is. Now, if I go over here and I go on the one that's got less of a kink, it's only 22.5. And if I go here, it's also going to be 22.5. So my pressure goes down. But if I add all the pressures up, if I add the pressure here, 22.5, plus this one, 22.5, that's 45. And then this 45 plus 45 equals 90 volts. So my pressures are going to get divided in a series circuit. Big ideas with a series circuit. Number one, they're all hooked up in a line, and there's only one pathway for the current to go. Number two, if you do something to the current here, it affects it around the entire circuit. You can't not affect the whole thing. These are like old school Christmas lights. I don't know if you ever had any of those. If you had one Christmas light that would go out, the entire circuit would go out. Let's talk about parallel. All right. This is a parallel circuit. Now, I'm going to build this circuit two different ways, and they're going to behave the same. So here's number one. I'm going to hook this up, and you'll see with a parallel circuit, we talked before that a parallel has more than one pathway. More than one pathway for it to go. And let me explain to you how the more than one pathway works. If you follow these electrons, you'll notice that it has a choice. The electron can go up through the top resistor, it can go straight through the middle resistor, or it can choose to go down through the bottom resistor. And because each of these right now is the same, 10 ohms, 10 ohms, and 10 ohms. They're all the same. I'll make this 10 volts just to make nice easy numbers. You'll notice that every third one, the first one goes here, the second one bottom, top, middle, bottom, top, middle, bottom, top, middle, bottom. They're choosing equally. The same amount of electricity, electrons, current, is traveling through each of these. And I can show that using an ammeter. I can say that, oh, there's 1 amp flowing through here, 1 amp flowing through here, and 1 amp flowing through here. Now, if I make this, I'm going to make this one twice. Now I'll go like this. I'll make this one 40, and you'll see immediately that not as much is going through the top one anymore. You're going bottom, middle, bottom, top, middle, bottom, middle, bottom, middle, bottom, top. So like every fifth or eighth one is going up here. I'll make this one 20 ohms. Now, so now you can start to see that when I adjust these, different amounts of current are going through each one. I still have that 1 amp going through here. See how it's still 1 amp? Now I have, this one's twice as much resistance, so check it out. Half as much current is flowing through there. And this one here is half of that, so you're getting 0.25. So in a parallel circuit, these all have the same pressure. My battery is pushing on each of these the same. But because this one's easier to go through, more electricity is going to go through it. And I'll show you that I'm pushing on them the same. Check this out. I'm going to put and measure the voltage right here. Did it backwards. 10 volts. I'm going to measure the pressure across this one. 10 volts. I'm going to measure the pressure across this one. 10 volts. The pressure is the same regardless. But what's different is the amount that goes through it. I like to think of this, if you ever had, as a kid, you had that Play-Doh Fun Factory. This is similar to like the Play-Doh hair salon. Like, I want to show you this video. Maybe you had this as a child, or maybe you know somebody with it, where you take this and then you push through it. This is like a parallel. This is a parallel right here, because the Play-Doh is being pushed on, each of these equally, but some of these have a really big hole, so more Play-Doh flows through it than the smaller ones. This is a really good example of a parallel connection, how they're all being pushed on equally by the battery, or the crank, but then they just have a bigger hole on some, so you get more Play-Doh flowing through. Same idea. This battery is pushing equally across all these, but because one has less resistance or a bigger hole, more Play-Doh is flowing through it. Now I'm going to rebuild this exact same circuit a different way and see if you can see the similarities and differences, because you see it in this way, you're like, oh, I can see the streets where it can either go north, it can go straight east, or it can go south. You know, I can choose here. But I'm going to draw this and build this circuit a different way, and I want you to see what it looks like. Here is that exact same circuit that I had before, just built in a little bit different way. So I still have my 10-volt battery here, and check it out. I have it drawn in a different fashion. This is the exact same thing. They're all 10 ohms right now. So I'm going to make this one 10. I'll make this one 20. And I'll make the last one 40. So here I've got a choice again. The electrons are coming out of the battery. They're being pushed. And these electrons could turn right and go through this one. They could go straight and go through this one. Or they could go straight again and go through the last one. And if you look, you'll see more traveling through the one with the least amount of resistance, 10 ohms. This one's 20, and this one's 40. So if I were to measure that current, you're still going to see 1 amp going through here, that half of an amp going through this one, and then that 0.25. Now what's interesting is this, like if I take this one and I increase the resistance, notice how it's not changing this one. They're almost independent of one another. Bring that down to 20. And here's another cool thing. If I somehow disconnect this one, doop, look at, electricity still has a pathway for this to go, right? So I could disconnect this one too. I still have a pathway. So if you break paths in parallel, it doesn't necessarily turn the whole thing off. Now, if I cut it off right here, I can shut them all off. So this is how your room is wired. Instead of these being like resistors, you could just as easily replace them with light bulbs. And this is how my classroom, your houses, this is how they are all wired. This is how they're all wired. Let me quickly do this. So now, put my light switch in, and I close it, and now I can turn on the lights everywhere. All of them are controlled by this one switch. And if one light bulb burns out, boop, the other ones are still working. Now, your house, maybe you have plugged in a bunch of things and had all the power to your room go out, and that's kind of how your house will work. So I'll put a fuse in here to protect my house. So right now, I think this fuse will blow at 4 amps. So check this out. If I keep adding things, like here I'm going to plug in a blender. So we'll put in another resistor. And I'm going to monitor my current. Let's see how much current I've got going right now. I've got 2.99 amps flowing. So I'm going to plug in my blender, which is basically another resistor, something. Boop. Oh, I went to 3.98. If I plug in one more thing, uh-oh, that's not going to be good. My drawing's getting a little bit hairy here. Watch what happens if I plug in one too many things. I have a sneaking suspicion. Pop! My fuse blew. So if you're at your house and you plug something in, everything goes off, it means downstairs in the basement at your circuit panel, there's a circuit breaker. You have to, number one, you have to unplug something. Because if you flip that breaker, let's wonder if I can reconnect it here. Okay, things are good. But if I plugged that one extra thing in, it's going to blow the circuit again. So if you go back and reset this, oh, it blows again because you have to unplug something. You're pulling too much electricity through your wires. And your wires, if they have too much electricity going through them, they can burn and start a fire inside your walls, which is bad. So this is what I wanted to show you. A little bit of difference between series and parallel today. What is similar about them? What is different? And we'll talk more about them specifically with numbers and things tomorrow.